Okay, let's continue our discussion of conservative fields here. Let's take this case. Is this particular vector field e to the x cosine y I plus e to the x sine y j equals f bar conservative? Okay. All right. We've actually considered this before, believe it or not, but let's take a look at it. Okay. Let's remember this statement here. If I've just got m and n, okay, ij, right? I'm just dealing with a vector field in the plane, then it's going to be conservative if and only if the curl is 0 over a simply connected domain, which is what we're going to always have here. Okay? In this case where you take the curl, you can see the curl always ends up being in 2 dimensions. We said n sub x minus m sub y k. That's going to be 0 if and only if n sub x equals m sub y. So that was that shortcut in the case of dealing with a function in 2 dimensions. We've got a little bit shorter way of making this statement here. Okay? All right, well, first of all, let's go ahead and talk. The domain of this thing is the entire xy plane. That's simply connected. There's no holes in that. Any simple closed curve can be continuously shrunk to a point without leaving the domain. Okay, the xy plane in this case. Okay, let's talk about this. Let's go. No, I guess we didn't do this one. It was so closely related. Come to think on it. Anyways, n sub x is e to the x sine y. That means n sub x is n of xy equals e to the x sine y. N sub x is therefore e to the x sine y. M sub xy is e to the x cosine y. M sub y is negative e to the x sine y. These two are not equal, as I state here, so the field is not conservative. Okay? So that would mean if you're going to integrate along a curve, right? If you're going to integrate around a circle, for example, generally, not always, but generally you would do what? Get something other than 0. Okay? Let's look at a different one here. Here I've got another field in 2 dimensions here. We'll look at a 3-dimensional one here in a minute. Okay? I've got 6x plus 5y j I plus 5x plus 4yj. The domain here, as you can see, is the entire xy plane. M is going to be 6x plus 5y. N is going to be 5x plus 4y. M sub y would be 5. N sub x would be 5 also. These two are equal everywhere in the domain, r squared. So the field is conservative. What does that mean then? That means it's a potential field. There should be a potential function whose gradient gives rise to a cap f bar. Okay? If we have little f being that potential function, the gradient of f in 2 dimensions would be what? F sub x, f sub y. Those would be the I and j components respectively. That would supposed to be equal to what? 6x plus 5y here. That's the I component of f bar. The j component is 5x plus 4y. So for these two vectors to be equal, we have to have what? F sub x is equal to that guy, and f sub y is equal to that guy, right? Okay? Now, let's go ahead and let's do like we usually do. I'm going to have a slight change in this one. I'm going to find f sub x here. I'm going to integrate the m with respect to x, like usual, a partial integration. You can see that would be what? 3x squared plus 5xy plus any function, an arbitrary function of g. So we've got this. Okay? And then I'm going to do it a slightly different way. Some people like doing this better. Let's come back here and let's do this on the same footing here. F sub xy should be what? The integral of the n with respect to y. That would be what? 5xy plus 2y squared plus an arbitrary function of x, right? Okay? But these two are supposed to be equal, right? This whole thing is supposed to equal this whole thing. How could that be? Okay? Now remember, it's important to remember g sub y is a function of y alone. Okay, so g sub y couldn't correspond, for example, to the 5xy. Okay, all right. Well, here's the idea. And of course, now the h of x is a function of x alone. Okay, so do you see what the h of x is while we're pointing at it? That would correspond to what? The 3x squared. The 5xy, these correspond to each other. And then the g of y corresponds to the what? 2y squared. Okay, so substitute those facts in there. We neglected to add any c on here. Usually pretty much never matters anyway. Okay, but you could, if you wanted to, you could add c to both of these. And there you go. Okay, but this then must be our function. F of xy is 3x squared plus the 5xy plus the 2y squared. So this was our h, and this was our g, and this we got from the integration here. Okay? All right, now you can always double check your answer just by doing what? Finding the gradient of little f here and see if it doesn't correspond to your original field there. And it does. Okay? Okay, what am I going to use this for? Well, suppose I'm integrating this thing, right, over some curve C, where C is a smooth curve, some smooth curve, connecting negative 1, 1, and 2, 3. Okay? Well, you got to come back here. You see that our f here is the same as our previous f, right? dr bar would be to the dx dy, so when I take the dot product there, I end up getting that expression right there. Okay? Just a reminder of what our field was, right? This is our field. Okay? All right, well, if I dot that with dr bar, I get precisely this, right? This thing. Okay? Alrighty. Well, you know what's it? You're integrating over a conservative field. So it's not going to matter this time what curve you actually integrate over, right? You're going to get the same value. It's independent of the path from negative 1, 1 to 2, 3. Doesn't matter. Okay? Doesn't matter how I do it there. Okay? Now, what you could do, you could, what? Actually, just knowing that it's independent of the path, you could connect a straight line between the two of these and integrate that way, like we did on a previous problem. You know, you could do that. But instead, you know, we already found what? We already found a potential function for our field, right? We already found it. We found this guy right here, right? Well, I didn't go to that work for fun. Let's go ahead and do this, okay? Well, what does our fundamental theorem of line integrals say? Well, you just have to take that potential function and what? Evaluate it at the endpoints and take a difference, okay? So make sure you do these in the right order though, right? You're starting at negative 1, 1 and ending at 2, 3. I made those substitutions and I ended up getting 60 for the value of my integral there. Okay, so that's the idea. Okay, independent of the path because it's a conservative field. Let's do one in 3 dimensions here. Okay, f is yz, xz, xy. Those are the I, j, k components respectively. The domain, as you can see, would be what? The entire space, right? All of 3 space. We're going to need to absolutely use the curl this time. Let's try the curl here. So before I even try to look for a potential function, let's test and see if it's even conservative. Okay? All right, the curl of f. Okay? So we will put in the components like this, and then we've got our partial derivatives. Again, for those people that want to put the I, j, k up there. Okay? But we find the curl here, so we would be doing that, what, this minus this, okay? So we would get x minus x in this one, okay? The difference here minus the difference there and so forth. That would be y minus y, okay? And then the very last one, z minus z is 0. We got the 0 vector. It's conservative. What does that mean? That means there ought to exist, what? A potential function whose gradient actually gives us this particular field, f bar. Okay? All right, so let's say a little f of x, y, z this time, right? In 3 dimensions, don't forget, is the potential function. We just gave it that name. Okay? Then we would have what? What's the gradient of little f? It's f sub x, f sub y, f sub z, right? In that order. That should correspond to yz, xz, and xy. Okay, let's find little f. We're going to integrate with respect to x, and we would get what? xyz plus some function, any function, I should say, of y and z, right? Does that make sense? Okay, because any function of y and z, if I differentiate with respect to x, holding y and z constant, this would zero out there, wouldn't it? Okay, that would zero out. Okay, now I thought about doing it this way. Okay, let's go ahead and differentiate. Now I have kind of a general form for f, right? I'm going to differentiate it with respect to y. Okay, what would we do if you differentiated this with respect to y? Right here, you would get xz. Right here, you would get g sub y of yz. Okay, g sub y of yz. That's the partial derivative of g with respect to y. Okay, but wait a minute. What is f sub y supposed to be? F sub y is supposed to be that function right there, right? It's that component, xz. Okay? So I've got what? xz plus g sub y is x sub b. What does that imply about g sub y? That means it's got to be 0, right? That's got to be 0. Okay? What does that imply about g itself? Okay? Well, I could imagine integrating with respect to y. That means my leftover g here is a function of z alone. So I actually have, when I combine that fact up here, I actually have that my f now looks like this. xyz plus some arbitrary function of z. Now, I need to deal with that arbitrary function of z here. All right? Well, let's see how we do that. Well, I'm going to take f sub z, so I'm going to differentiate with respect to z, right? So if I did that on this previous function, remember it's x, y, z, if I differentiate that with respect to z, I would get what here? I would get xy out of that, and I would get what? Z prime right here, right? Okay, so that's what I've written here, xy plus z prime. But wait, what was f sub z supposed to be? F sub z was supposed to be xy. Okay, so I get xy here. So I've got xy plus g prime of z is xy. That means g prime should be 0. That means g of z should be just a constant. And a potential function for us would be what? xyz plus any arbitrary constant. Okay? Now, let's say I was interested in computing the line integral of, and let's bring this up here, the line integral over some c, and all I know about c is that it's smooth and has endpoint 0, 0, 0, and 1, 2, 3. So I'm going to be going this way, from 0, 0, 0 to 1, 2, 3. Okay, so let's say we go that way. Well, we know we're dealing with originally a conservative field. And do you see that this is our field, right? This is f bar that we were dealing with, dotted with dr. That's exactly f bar dotted with dr, dr bar. Okay, I gave that a name, line integral L. Okay, now what do you say? What are we going to do? Well, we found this is a conservative field. It should be independent of the path. Thank goodness, because if it wasn't, I don't have enough information to actually integrate this, right? Okay, if you're not dealing with a conservative field, usually, I mean, you'd have to know exactly what the path is, because you can't, not just the endpoints, it matters which path you take generally, but not in a conservative field. Okay? All right. F here, our little f, was this guy, remember? So all we have to do, okay, we added a c, but that's going to cancel out. We don't care about that. All we have to do is what? Evaluate that at the terminal point and what? At the initial point, and take the difference in that order. Okay, so we can do that in our heads. That's 6 minus 0. So the answer is 6. So the value of this integral, that L, is actually equal to 6. Okay, very cool. Sounds easy. Okay, let's do one more problem of this type here. Okay, this should look familiar here, right? What is this an example of? Right, a centrally directed field in inverse square law. Do you remember we found that this is conservative? Okay, this is actually, we found this when we were first talking about potential functions and gradients and stuff here involved with this stuff. We found this is actually a potential function for that. Okay, you can go back and look in a previous video for that. Yep. Okay, if I was to find the gradient of that, I would end up with what? That right up there. Okay, now let's say I was going to do work. Okay, let's say I'm going like this. I've got some unit vector pointing in a certain direction. Okay, so there's the direction. I'm going from some position A, little scalar A times U, okay, out to what? B times that U. Okay, so this would be directed straight outwards from the origin. Okay, ready? And I wanted to consider work then. What would I do? Well, think, this is what? Force dotted with differential change in position, right? Well, we know that's a conservative field, so we just have to take the potential function here and do what? Evaluate it at the endpoints and take the difference. Okay, like that. All right, that would be the total work done. Force dotted with differential displacement, right? Okay, now if you actually evaluate that, remember k is constant here, so we would get k over the magnitude of b u hat minus k magnitude a times u hat. These are positive, by the way. Okay, I should have said that, even though I wrote it there. And then I've got this, right? Because we know the magnitude of u bar, or u hat, is 1, so we've actually got this, okay? And what's a way of writing that? That's another way of writing that is to get a common denominator, AB. So we've got k times the difference between A and B divided by the product AB. Okay? Now, let me just explain where you've seen something like this happen here in a gravitational field. Let me get rid of this. I'm sorry, I need a little real estate here. Okay? What if I'm moving an object directly away from the Earth's surface? Okay, so I imagine, the surface being a sphere, and I'm moving right away from the center, so normal to the surface of the sphere. Okay, K, AB is really close to K over the radius of the Earth squared, right? Darn it, squared. Sorry for the break there, I had a technical glitch. Anyway, what I was saying here, if I'm moving this object and we're just moving it directly upwards close to the surface of the Earth, okay, so I didn't move it very far here, then I want to look at this expression here. The A and the B are really close to the surface of the Earth, then, or if we're moving really close to the surface of the Earth, then A and B are both almost the radius of the Earth, right? So I'm going to put this approximately A minus B K over R squared, and then we want to consider here, okay? All right, now let's take a peek here. So we've got this expression for f. I want to come back here real fast. Can you see here, because I'm talking about the force between maybe the Earth and some object here, that K would actually be what? The product of the gravitational constant, the mass of the object, and the mass of the Earth, which I'm calling E there. Okay? And so what would our work look like? It would be A minus B times our K here, which is the G, M, cap E over AB, which is approximately A minus B times little m, GE over R squared. Okay, this is where there's the approximation we were talking about just earlier. GE over R squared. What is this equal to? This is actually equal to the acceleration due to gravity close to the Earth, which is often written little g, right? 9.8 meters per second squared. So the work is approximately equal to, mg times the difference in the height. Well, do you remember working baby problems in physics where you talked about the work? What did you do? The work lifting an object a short distance on the Earth, what did you do? The mass times the acceleration due to gravity times what? The actual height that you ended up moving the object. Okay? So this is the idea that we see happening right here. Okay? Alrighty. Now, one last thing here. I just wanted to go back and do a quick proof here of why this is even working here for our fundamental theorem. Suppose that I have an integral like this, a line integral. Okay? And so we imagine our f here being a gradient field, so conservative here. So we've got that. Okay, so I've written it this way. Okay? Now what is a gradient? Here I'm doing it in 3 dimensions, the full 3-dimensional version. So that's what? The vector f sub x, f sub y, f sub b, f sub z, right? Dotted with d r bar yields this thing right here. Okay? And then we're integrating over some c. Now what I'm going to do is imagine what? C is going to be parameterized, so my curve C is nice and smooth, and it's going to be parameterized by, say, t. Okay, so we'll be, here's our C here. We'll be going from the initial point at t1 to the terminal point at t2. Okay? All right. Okay, well, if this is a parameterized curve, then we imagine what? That x is a function of t. So x equals x of t, y is a function of t, and z is a function of t. Then I can actually rewrite this integral, thinking about it as an integral in terms of t here, where I factored out dt here. Okay, and you should be familiar with expressions of this kind, right? Oh, crap. Let's go back and put that back. Okay? Don't be so hip on erasing there. There we go. That's what I want to do. Anyway, okay, you should be familiar with expressions of these types. Does that recall the chain rule too? I hope it does. This would actually be what? This would be the integral from t1 to t2. This expression right here is actually, if you think about it, from the chain rule, that's the derivative of f evaluated at what? X of t, y of t, z of t, right? Remember how the chain rule worked there. Okay, we're imagining, of course, x is a function of t, y is a function of t, and z is a function of t along our curve here, right? Along that guy. Okay, we imagine that being our parameterized curve. Well, wait a minute. From the fundamental theorem of calculus from Calc 1, this whole thing's a function of t, right? We just imagine that being a function of t, and it's a differentiable function of t, no less, as we can see right here. So when we find an antiderivative, that would just be what? Our f evaluated at x sub t, y sub t, z sub t, and then it's going from what? T1 to T2, and then we have our result here. This is essentially what? F evaluated at the terminal point, right? All right, because we usually don't parameterize the curve, particularly in the case where you're dealing with a conservative field. So you're taking f at the terminal point coordinates. We usually just take the coordinates, right? X2, Y2, Z2, say, and then minus what? The function evaluated at the initial point, maybe X sub 1, Y sub 1, Z sub 1. Okay, and there it is. There we have our result. Alrighty? Okay, well, I hope this helps.